Now, earlier we have discussed the limit of sequence of the real numbers. Now, in this lecture we will see how the limit of the sequence of the functions can be introduced and whether the corresponding results which are valid for the sequence of real numbers can also be valid in case of the sequence of functions of real number when you take the limits. In the form, let A, which is subset of R, let F and G, which are the mapping from A to R, and let C belongs to R be a cluster point of A, Suppose that f x is less than or equal to g x for all x belongs to A, that is for all x belongs to A, but x is not equal to c, x belongs to, but x is not equal to c. Then limit of this function f x, if limit of f x when x tends to c is infinity, then limit of g x when x tends to c will also be infinity. And B part is, if the limit of g x when x tends to infinity, x tends to c is minus infinity, then the limit of f when x tends to, then limit of this x tends to c will be minus infinity. Of course, this obviously one can say. So, we are just skipping the proof for it and then. Okay. Now, so far we have taken when L is infinity, is it not? L is infinity and then we have chosen this part. Now, one sided limit of this definition, let A belongs A, which is a subset of R, and let F is a mapping from A to R, and if C is a crystal point belongs to R, be a crystal point of A of the set A intersection C infinity. That is the left hand limit and right hand limit. We are giving the concept here. X belongs to A, where the x is greater than C. Then limit of this f when x tends to C plus is infinity means if for every alpha belongs to R, there is a delta depending on alpha positive such that for all x belongs to A, with 0 less than x minus c less than delta, then the f of x is greater than alpha for this. So, this is the left hand concept of the limit. The limit of the f from the right hand side is infinity means that if I picked up a set A intersection C infinity and C is the crystal point of this set, then we say the limit of the function when C approaches towards the right hand side or right hand limit of A is infinity means that we can identify a delta corresponding to every alpha such that the f of x will exceed by alpha for all x satisfying this condition. Similarly, when it is the negative side, then we say simply if it is negative say minus, then what is changes here is the corresponding c, it will be infinity c, that is minus infinity c, and then from here minus infinity c, and from here it will be just a c minus x, 0 less than x less than delta, then it will come to be f x less than alpha, like that. So, similarly, the changes will be like this accordingly. We are not giving that. Okay. Then, for example, is this, say 1 by delta f x g x equal to e to the power 1 by x when x is not equal to 0. Now, this we have already seen that if we take for any delta for any point, any interval 0 delta, where delta is positive, the right hand side limit of this function tends to this right hand, when x tends to delta, right hand side tends to infinity as x tends to 0 plus, and this limit goes to 0 as x tends to 0 minus. This we have already discussed it, limit in. Okay. Now, next concept, when c, one of the limiting point c is not finite. If it is infinity, then also we can define the limit as follows. So, limit at infinity, we can say the limit at infinity concept, limit at infinity, limits at infinity. Okay. When we have the limiting point c is infinity, we define as follows. Let A be a subset of R, non-empty subset of R, and let f is a mapping from A to R. Suppose that A infinity is contained in A for some A, for some A belongs to R. Suppose this interval, then we say, then the limit of this f when x tends to infinity L means that for a given epsilon, means for given epsilon greater than 0, there exists a k which depends on epsilon and greater than a number. This k greater than a, such that for any x greater than k, any x greater than k, the f of f x minus L, if for given epsilon there exists such that for the thing f of x minus L is less than epsilon. Then we say the limit of this function f when x tends to infinity is L. So, when x is sufficiently large, means at the infinity we are touching finding the behavior of the function f x. Function f x, what is the behavior of the function at the point at infinity? This shows the limit. Okay. Then plus infinity minus infinity also in a similar way we can write. Then another result plain true, let A which is subset of R and let f is a mapping from A to R, and suppose that A infinity is A infinity is contained in A for some A belongs to R. Some, then the following statements are equivalent. Then following statement are equivalent. The first statement says the limit of this function f when x tends to infinity is L, and second statement says that for every sequence for every sequence x n in a intersection a infinity such that limit of x n as n tends to infinity is infinity. Then the sequence f of x n converges to L. So, this is the equivalent definition in terms of the sequence. When we say limit f as x tends to infinity is L, then in terms of the epsilon delta definition we have taken that for a given epsilon we can identify a k such that when all x greater than k, the difference f x minus L will be small. And for a sequence, if in terms of the sequence we can say there exists a sequence x n which are tending to infinity, and then the corresponding functional values will converge to L, close to L. So, that is the equivalent definition for the. Okay. Now, if when both the limits plus in c is also infinity, a is also infinity, then we define the concept as follows. Let A, which is a subset of R, and let f from A to R, suppose that A infinity, this is contained in A for some A belongs to A, for some A belongs to A. Then we say f tends to infinity as x tends to infinity, we say f tends to infinity as x tends to infinity, that is we write like this: limit of f when x tends to infinity is infinity if given any alpha belongs to R, there exists a k depends on alpha greater than A such that for any x belongs to x greater than k, for any x greater than k, then f of x will be greater than alpha, okay, greater than alpha. So, this is the concept when both the means c is also infinity and L is also infinity. Similarly, we say if we take limit of f as x tends to say infinity is minus infinity, x tends to infinity is minus infinity. It means as x tends to infinity means for any alpha there exists k greater than alpha k depend on alpha such that k alpha is greater than 1, then for any x greater than this it will show f of x is strictly less than alpha. So, that will be the criteria when x tends to infinity, f is minus infinity, this two. Again in the sequential form we can say like this. So, equivalent concepts in the sequential criteria, that is in the form of theorem. Let A belongs to R and let f is a mapping from A to R, and suppose that A infinity is contained in A for some A belongs to R. Then the following statements are equivalent. The first statement is limit of the f as x tends to infinity is infinity. And second statement says for every sequence x n in a infinity such that limit of that sequence x n when n is sufficiently large is infinity, then the limit of this limit of f of x n as n tends to infinity will be infinity, limit of this. So, this is the equivalent concept. If suppose we want that one limit of this is minus infinity, if the limit of f when x tends to infinity is minus infinity, equivalently we can say here is for every sequence x n in a infinity such that limit of the x n is infinity, then limit of this f of x n will be minus. Then here limit of the f of x n as n tends to infinity will be minus infinity. This is the equivalent way, equivalently respectively, or we can say this clear. So, concept is this one. Now, one more results which will help in getting the sometimes limits. Let A which is subset of R and let f g are the mappings from A to R, and suppose that A infinity open interval A infinity is contained in A for some A belongs to R, for some A belongs to R, and suppose that g x is always positive for all x greater than A. So, these are the restrictions we put it, and that for some L, and that for some L which is in A R, L is not equal to 0. We have one. We have first is limit of this f x by g x when x tends to infinity is say L. This can then depending on L we can identify the limit for f and g. So, first condition said if L is positive, then limit of f as x tends to infinity will be is infinity if and only if limit of g as x tends to infinity is infinity. So, if L is comes out to be greater than 0, then both these function f and g when x is sufficiently large will be infinity, the value will come out to infinity. And second is if L is negative, then limit of f if this is in as x tends to infinity, if this is minus infinity, if and only if limit of g is plus infinity. That is, if L is negative and limit of g is positive, then limit of f will be minus infinity. If limit of f is minus infinity, then limit of g will be infinity if L is negative. But if L is positive, then if f is limit is infinity, g will also have a limit infinity, and similarly vice versa. If g is as limit infinity, L will also have a limit infinity. The proof of this, see the proof for this is not difficult. Say first, given that L is positive. Okay. So, once L is positive, then and A belongs to this. So, let us take A 1 which is greater than A belonging to the interval 0 A to infinity, this interval which is such that f x by g x, because this limit is L. So, if I choose the epsilon as L by 2, choose epsilon as L by 2, then we can write this thing as f x by L is lying between 3 by 2 L greater than, because f and g both are giving to be a positive, g is also positive. Okay. So, if this we can write it f x and g x as greater than half L of L, and when x is sufficiently large which is positive. So, we can, since L is, we can suppose there exists A 1 such that this condition hold. Okay. By this is our way. Okay. Such that this condition hold. Therefore, what will be, so multiply by g x, because g is given to be positive. So, multiply by g x, we say here is multiply by g x, we get half L into g x will be less than f x, will be less than 3 by 2 L into g x, and this is true for all x greater than A 1. So, obviously, this will be true for. Now, take the limit. What is now change is, if f is infinity, then g is infinity. So, here if f is infinity, g will be infinity. If g is if g is infinity, f will be infinity. If f is infinity, from here g will be infinity. So, follows. So, result follows. Okay. So, this will be the one. Now, let us see some examples based. We have x to the power n, another form we have already discussed, that if function f x is x to the power n, then limit of this function f x, that is x to the power n when n tends to infinity, the limit of this when x tends to infinity, when x tends to plus infinity or x tends to minus infinity, that way. So, if I take the x tends to minus infinity, then when n is even number, this will go to plus infinity also, this will go infinity if n is even, because x is tending to minus infinity, but n is even. So, it will, and when n is odd, then this will go to minus infinity. So, we can get it, and this condition. Similarly, if the polynomial p x is given, say a n x to the power n, a n minus 1 x n minus 1 up to say a naught, then limit of this p x when x tends to plus infinity, this will be equal to infinity if a n's are positive. A n's are positive. Okay. A n's are positive, and p n will be negative minus infinity if a n's to be negative. So, this can be proved like this. Okay. So, in case of fraction also we can do it this way. Thank you.